what can we say about time evolution of this observable mean energy of our flow? And this, as far as I can tell, was done by Reynolds in something like 1898, or in early 1900s. And for that reason, in literature, it's referred to people who did it 2 years ago or 5 years ago. In a professional journal like Journal of Fluid Mechanics. So let's take the derivative of this energy, E dot. That's expectation value. So if I compute E dot, I just get expectation value of U times U dot. But I have an equation for U dot. That's my equation of motion. This thing right here. So I can substitute it, put all these terms in, and I get that is minus this minus here, space average of the function u squared over 2 plus ux plus uxx is the x derivative times u. I can use my integration by parts rule and just move this derivative over there. And now look at this, and I notice that this thing here is really just u cube derivative. 1/3 of. So this whole part is again a full derivative. So this goes away. This is square or something, so it's not going to go away. It's a positive number. No, I should remove it. And here I can again use integration by parts to move one of the derivatives over here, and I'll get minus uxx squared. That cannot vanish either. So what do we get? We get that the energy, mean energy in our system, plane front and energy being interpreted as the motion of the front itself, velocity square, in time, has two contributions, and we'll give them names. One we'll call power, the other one we'll call dissipation. Where by power we mean this gradient ux squared. And remember, that is the mechanism in which we put energy into the system in Kuramoto-Shibashinsky. It has a wrong sign, this guy. It's anti-diffusion in here. Minus the curvature of the whole thing squared, or Laplacian of the whole thing squared. And the reason why I call them power and dissipation rate is that when we rework this exactly in the same way, like Reynolds and Orr did a long time ago, for three-dimensional Navier-Stokes flow, we will see that there's always a term which is our forcing term. And it tells me how much energy I put per unit time into the system. And then this term will be called entropy. It'll be square of the curl of the flow, and it'll have interpretation as energy dissipation. Both things, everything here is time dependent. This is a very useful probing flows, especially if you're doing numerical simulation, because intuitively you do care about episodes when you're burning lots of energies, and there are other episodes where you have to put energy in a flow to maintain its motion. So for example, if you have a pipe and you're trying to move fluid through at constant mean velocity, because you want to get a liter of fluid per second at the other end, then what happens when you have turbulent motions? There are episodes when the vortices of the fluids are working against you and you have to push harder instantaneously. So this power will have to vary to compensate for the fluctuations in the friction of the fluid. And then that energy has to be lost on its own time scale. This dissipation is burning the energy. Typically what happens here, we have the body forcing because we are saying that depending on the shape of our wavefront, we force it that way. Typically in fluid dynamics, what you have is you have some kind of walls and you move them. That's called shear flows. So this term here will come from the boundary terms in this integration. And they'll tell me how I put energy into the flow. And this term will turn out to be a volume integral, like we have right now. And they'll tell me how I burn the energy in a dissipation, how it goes from mechanical motion to heat. That's what Laplacian does, the viscous term in Navier-Stokes. They're also very nice for other reasons. They're somewhat physical. They're measurable things, how much energy you put out and how much you heat the thing, at least in principle. And also from theory's point of view, when you do numerical simulation, when you examine these terms, you realize that they're invariant under symmetries. So all these painful things we had to do with symmetry reduction, slices, finding fundamental domains, they're irrelevant for this computation because you just compute quantities which are correct any co-moving frame,